The eastern plains of Dakota Territory hit different in the spring of 1875. John Thatcher learned that his first winter, when his wood shingled cabin leaked through 3 storms, and his neighbor Samuel Korff had to replace his entire roof after snowdrifts collapsed the standard framing. Thatcher had built his homestead exactly like every settler on that open prairie was told to build. Wood frame cabin, cedar shingles, raised quick for farming season, standard and trusted. By his second winter, he was splitting more shingles and patching more leaks than any man should need. Across the territory, homesteaders were fighting the same losing battle with roofs built by the book and failing every 5 years. His neighbors mocked him when he quietly turned to an old technique that used the prairie itself as his roof material. What did this one homesteader understand about building on open land that outlasted conventional wisdom by 20 years? The quarter section John Thatcher claimed that spring stretched flat toward the horizon, with only occasional cottonwoods marking creek beds and buffalo wallows. Timber meant a 3-day wagon trip to the river bottoms, and even then, the available wood ran to scrubby oak and soft pine that split under the constant prairie wind. Most homesteaders solved this by ordering pre-cut lumber from Yankton, but that meant paying freight costs that consumed half a season's crop money before the first furrow was turned. Samuel Korff had explained the accepted method when Thatcher first arrived. Frame your cabin with 2 by 6 inch lumber, space your rafters at standard 24-inch centers, nail on 1-inch pine sheathing, then cover with split cedar shingles. The whole system could be raised in 10 days with help from neighbors, leaving time to break sod and plant wheat before the short growing season ended. Every homesteader manual recommended it, every lumber dealer stocked the materials, and every carpenter knew the techniques. But the mathematics of prairie weather told a different story. Winter storms that built over 1,000 miles of open grassland hit with wind speeds that flattened corn stalks and drove snow horizontal. When that wind-packed snow accumulated against roof lines, the load could reach 40 pounds per square foot, nearly double what forest country cabins carried. Korff learned this the hard way when his rafters sagged under a February drift that buried his eaves and cracked his ridge beam. 2 homesteads down, Mary Wright discovered another flaw in the standard system. The cedar shingles that worked fine in timber country dried and cracked under the relentless prairie sun, creating gaps that let wind-driven rain penetrate to the sheathing. Within 3 seasons, her roof deck had developed soft spots where moisture rotted the pine boards. She spent 4 days that spring tearing off damaged shingles and replacing boards, work that kept her from her garden when every day of the growing season mattered. The pattern repeated across the territory. Roofs leaked, shingles blew away, frames sagged, and homesteaders found themselves re-roofing every 5 years whether they could afford it or not. The lumber dealers made steady profits, but families struggled under the constant maintenance burden that pulled labor and money away from farming. Thatcher had watched these failures through his first winter and recognized a fundamental mismatch. The accepted building wisdom came from regions where timber was abundant and weather patterns were moderated by forests. Here on the open prairie, with scarce wood and extreme conditions, following forest country methods produced forest country failures. The solution came from an unexpected source. Michel Leclerc, a Métis trader who wintered near the settlement, had built his cabin using techniques that combined French colonial carpentry with indigenous prairie wisdom. His roof had carried heavy snow loads for 8 seasons without failure, and his interior stayed warmer on less wood than his neighbors burned. When Thatcher asked about the difference, Leclerc pointed to the thick layer of prairie sod that covered his roof like a blanket. On the open prairie, you build equal to the wind and the earth, not just what you cut from the forest, Leclerc explained. The old-timers in his family had learned from Dakota builders who understood that the prairie itself offered the best materials for prairie conditions. Thick sod provided insulation that wood could not match, and the root systems bound the covering into a solid mass that wind could not penetrate. Thatcher had seen sketches of similar techniques in a Norwegian immigrant's journal. Scandinavian turf roofs used layers of birch bark and sod to create weatherproof coverings that lasted decades in harsh mountain climates. The principle seemed sound. Use the materials that grew naturally in the environment and build systems that worked with local conditions rather than against them. But adapting the concept to Dakota conditions required solving problems that neither the Métis nor the Norwegians had faced. Prairie sod was different from mountain turf, and the clay-rich soil held moisture longer than the sandy compositions used in Scandinavia. The root structure of buffalo grass created different binding patterns than northern sedges. Most critically, prairie snow loads and wind patterns created structural demands that had to be calculated correctly, or the entire system would fail. Thatcher began sketching his approach that spring. The foundation would be a pole roof frame using 8-inch diameter oak posts, spaced at 16-inch centers, nearly double the standard lumber frame strength. Over this, he would lay thick pine sheathing, then tar paper as a moisture barrier, then 12 inches of carefully selected prairie sod, with the grass facing upward to maintain the root system's binding properties. The neighbor's reaction was predictable. The lumber dealer warned that the weight would crush his rafters and the moisture would rot his timbers. Korff declared it backwards, thinking that would leave Thatcher living in a dirt-floored dugout, like the poorest Irish immigrants. Even Mary Wright, who had suffered through multiple roof failures, questioned whether covering a cabin with prairie dirt made sense when proper materials were available. Their skepticism reflected the deeper tension between conventional wisdom and traditional knowledge. The accepted method had the weight of printed manuals, professional recommendations, and familiar techniques behind it. But traditional knowledge, whether from indigenous builders or immigrant craftsmen, had been tested over generations in similar environments. The question was which foundation would prove more reliable when prairie weather put both approaches to the test. Thatcher recognized that his knowledge was incomplete. He understood the basic concept, but lacked details about sod selection, moisture management, and structural load calculations. The thickness of the sod layer, the proper root density, the drainage requirements, and the weight limits of his framing system would all need to be determined through experimentation and observation. But the repeated failures of conventional methods had convinced him that following standard practice meant accepting standard problems. The prairie demanded its own solutions, built from materials that belonged to the prairie and techniques that acknowledged prairie realities. Whether his neighbors called it backwards or progressive mattered less than whether it would keep his family warm and dry through 20 Dakota winters. That spring, he began gathering the materials and knowledge that would test whether traditional wisdom could outperform conventional methods. The sod roof system would either prove the value of building equal to the wind and the earth, or it would join the long list of frontier experiments that failed when theory met reality. The first structural test came in November of 1875, 6 weeks after Thatcher had finished his basic cabin frame. A neighbor 3 sections east, Wilhelm Brenner, had followed standard construction methods with 2-by-6-inch rafters spaced at the conventional 24-inch intervals. When an early blizzard deposited 18 inches of snow across the territory, then followed with freezing rain that created an ice shell, Brenner's roof began to sag visibly along the ridgeline. Thatcher rode over to investigate and found the mathematics of structural failure written in bent timbers and stress cracks. The ice-crusted snow had created a load of nearly 50 pounds per square foot, well beyond what standard prairie lumber could carry over the 12-foot span of Brenner's cabin. 2 rafters had developed hairline splits near the ridge connection, and the ridge beam itself had dropped nearly 2 inches at the center, creating a visible dip that would only worsen with each subsequent storm. The failure revealed a critical flaw in applying forest country framing to prairie conditions. Standard residential construction assumed snow loads of 20 to 30 pounds per square foot, reasonable for regions where trees broke up wind patterns and moderated accumulation. But prairie storms built momentum across hundreds of miles of open grassland, creating wind-packed drifts that could double or triple normal snow weights. When that load hit timber-sized for gentler conditions, the wood simply surrendered to physics. Brenner's problems multiplied when the spring thaw arrived. The damaged rafters had allowed the roof deck to flex during freeze-thaw cycles, loosening the shingle nails and creating gaps where water penetrated to the interior. He spent a week that April tearing off damaged sections and sistering new lumber alongside the split rafters, work that cost him $12 in materials and 40 hours of labor during planting season. Thatcher understood that his planned sod roof would create an entirely different structural equation. 12 inches of prairie sod, saturated with spring moisture, would weigh approximately 80 pounds per square foot before any snow accumulation. Add winter snow loads, and the total weight could reach 120 pounds per square foot, nearly 4 times what standard framing could handle. Building with conventional lumber would guarantee the kind of catastrophic failure that had damaged Brenner's cabin. The solution required abandoning lumber framing entirely and adopting techniques designed for heavy earth loads. Anders Hansen, the Norwegian housewright who had settled 2 townships south, had brought knowledge of Scandinavian turf roof construction that used massive timber posts rather than dimensional lumber. When Thatcher visited Hansen's homestead that summer, he found a roof structure built with 8-inch diameter oak posts, spaced at 12-inch centers connected by equally heavy ridge beams and plates. Hansen explained the engineering principle behind the heavy timber approach. Instead of trying to span long distances with slender rafters, the Norwegian system used closely spaced posts that carried loads directly downward through compression rather than bending. Each post functioned as a miniature column, transferring roof weight straight into the wall structure below. The system eliminated the long spans that caused standard rafters to sag and split under heavy loads. But adopting Hansen's approach required solving problems that Norwegian builders had never encountered. Prairie timber ran smaller than Scandinavian forest giants, and the available oak and cedar posts measured closer to 6 or 7 inches in diameter rather than the 8 to 10-inch timbers common in Norway. Thatcher would need to compensate for smaller timber by spacing the posts even closer together, reducing each post's load carrying. Requirement to match its reduced capacity. The calculations were straightforward once the principles became clear. If each square foot of sod roof would weigh 100 pounds when fully loaded with snow, and his available posts could safely carry 1,500 pounds each, then each post needed to support no more than 15 square feet of roof area. That meant spacing posts at roughly 16-inch centers in both directions, creating a grid of supports that would distribute the massive earth load evenly across the entire roof structure. Michel Leclerc provided another crucial insight when Thatcher consulted him about the wall structure needed to support such heavy roof loads. Leclerc had observed that earth-covered roofs created outward thrust forces that could push walls apart when the sod became saturated with moisture. The weight of wet sod didn't just press downward, it also pushed outward against the walls like water pressure against a dam. Standard wall framing, designed to carry vertical loads, could fail under this lateral pressure. The solution was a tie beam system that connected the walls across the cabin's interior, preventing them from spreading apart under roof loads. Leclerc showed Thatcher how to install heavy wooden beams just below the roof line, running from wall to wall and bolted securely to the wall plates. These tie beams functioned like the rungs of a ladder, holding the walls in their proper relationship, even when massive roof weight tried to push them outward. Installing the structural system required precision that standard cabin construction never demanded. Each 8-inch oak post had to be notched to receive the ridge beam and plate beams, with joints cut tight enough to transfer loads without slippage. The posts themselves had to be perfectly plumb and evenly spaced, creating a grid that would distribute loads uniformly across the entire roof area. Any variation in spacing or alignment would concentrate forces on individual posts and create weak points where failure could start. Thatcher spent 3 weeks that autumn installing his post and beam roof structure, taking time to measure twice and cut once on every joint. The work required skills that standard carpentry didn't teach, particularly the complex joinery needed to connect heavy timbers at multiple angles. He practiced the notching techniques on scrap wood before cutting his oak posts, recognizing that mistakes on 8-inch diameter timber could not be easily corrected. When the first significant snow arrived that December, the difference between old methods and new engineering became dramatically clear. Korf's repaired roof sagged again under 20 inches of wind-packed snow, requiring him to shovel the roof manually to prevent further damage. Mary Wright's cabin developed new leaks where her weakened rafters allowed the roof deck to flex. Across the settlement, homesteaders climbed onto their roofs with shovels and brooms, fighting to keep snow loads within the limits their framing could handle. Thatcher's oak post structure showed no signs of stress. The closely spaced posts carried their loads without visible deflection, and the tie beam system kept his walls perfectly aligned despite the massive weight pressing down from above. When he measured the ridge line after the storm, he found zero movement, zero sag, and zero indication that his structure was approaching its load limits. The engineering had worked exactly as the traditional knowledge predicted, proving that matching structure to actual loads produced better results than following conventional practice designed for different conditions. With his structural foundation complete, Thatcher faced the more delicate challenge of selecting and applying the prairie sod that would transform his cabin from a conventional shelter into a thermal fortress. The choice of sod material proved as critical as the engineering that supported it, requiring knowledge that no homesteader manual addressed and most prairie settlers had never considered. The key lay in understanding the different characteristics of prairie grass root systems. Buffalo grass, the dominant species across much of the Dakota Territory, formed dense mats with roots extending 18 to 20 inches deep, creating natural insulation panels that could be cut and moved intact. Blue grama grass produced similar root density but in thinner layers, while the scattered tall grasses like big bluestem created loose, less cohesive sod blocks that would not bind properly on a steep roof surface. Thatcher spent several days that autumn walking his quarter section, testing different areas by cutting sample blocks with his spade and examining how well the root systems held together when lifted. The best sod came from areas that had been heavily grazed by buffalo in previous years, where the constant trampling had created extremely dense grass growth with thick, interwoven root mats. These blocks could be cut into rectangles roughly 18 inches by 12 inches and 3 inches thick, maintaining their structural integrity even when moved and stacked. The application process required techniques that combined Scandinavian tradition with prairie adaptation. Hansen had described the Norwegian method of laying turf grass side down to create a weatherproof barrier, but Michel Leclerc argued for the opposite approach. Prairie sod laid grass side up would maintain living root systems that would continue growing and binding the roof covering into an increasingly solid mass. The grass itself would provide the first line of defense against wind and hail, while the roots below created the insulating layer that would moderate interior temperatures. Leclerc's reasoning proved sound when tested on a small section of Thatcher's woodshed roof. Sod blocks laid grass side up showed new growth within 2 weeks, with grass shoots extending through the surface and roots continuing to interweave below. Blocks laid grass side down began to separate at the edges within a month, losing the tight binding that held the covering together. The living roof approach required more initial moisture to establish the grass growth, but created a self-maintaining system that would strengthen rather than deteriorate over time. Installing 12 inches of sod over the tar paper required careful attention to weight distribution and layering sequence. Thatcher began at the eaves and worked upward in courses, each row of sod blocks overlapping the row below like enormous shingles. The first layer, placed directly on the tar paper, consisted of the thickest and most root-dense blocks, creating the primary insulation barrier. Subsequent layers used thinner blocks with less root density, building up the total thickness while maintaining the grass surface that would shed water and resist weather. The thermal performance differences became apparent within weeks of completion. During the first cold snap of November 1876, when outside temperatures dropped to 15 degrees Fahrenheit, Thatcher measured the interior temperature of his cabin at 62 degrees Fahrenheit near the center of the main room. At the same time, Samuel Korf's cabin with standard shingle roof measured 48 degrees Fahrenheit at the same distance from his stove, despite burning wood at the same rate. The sod roof's insulating effect worked both directions with equal efficiency. When summer arrived and outside temperatures reached 95 degrees Fahrenheit during the heat of July afternoons, the interior of Thatcher's cabin remained at 76 degrees Fahrenheit, while neighboring cabins with wood shingle roofs reached interior temperatures of 90 degrees Fahrenheit or higher. The thick earth mass absorbed heat slowly during the day and released it gradually at night, moderating the extreme temperature swings that made prairie summers nearly as challenging as prairie winters. Fuel consumption measurements provided the clearest evidence of the sod roof's thermal superiority. Thatcher carefully tracked his wood usage through the winter of 1876 to 1877, burning exactly 2 3/4 cords of split oak to maintain comfortable interior temperatures throughout the cold months. Mary Wright, whose cabin matched Thatcher's in size and orientation but used standard shingle roofing, required 4 1/2 cords of the same oak to achieve similar comfort levels, a difference of nearly 60%. The protective qualities of the sod covering revealed themselves dramatically during a severe hailstorm in June of 1877. Hailstones the size of hen eggs pounded the settlement for 20 minutes, stripping leaves from trees and shattering window glass in several cabins. The wooden shingles on conventional roofs showed extensive damage, with many shingles split or knocked completely off their nail fastenings. Horf counted 18 broken shingles that required replacement, while Wright found 7 areas where hail had driven completely through both shingle and roof deck, creating leaks that soaked her interior. Thatcher's sod roof showed no damage whatsoever. The thick grass surface had absorbed the hail impacts like a natural cushion, and the dense root mat below had distributed the forces so effectively that not even the tar paper underneath showed signs of puncture or tearing. The living roof had literally grown stronger since installation, with the grass roots creating an increasingly dense protective layer that could absorb impacts that would destroy conventional roofing materials. But the most significant advantage became clear during the routine maintenance cycles that plagued every other homesteader. By the spring of 1878, most of the wooden shingle roofs in the settlement required partial replacement, with homesteaders spending 3 to 5 days each spring replacing damaged or missing shingles, repairing leak damage, and recaulking gaps where wind had loosened the roof covering. Thatcher's maintenance requirements consisted of walking across his roof once each spring to check for any thin spots in the sod covering, and occasionally adding small patches where winter weather had caused minor settling. The work took less than half a day and required no purchased materials, only additional sod blocks cut from his own prairie. The roof was not merely maintaining itself, it was actually improving with age, as the root systems matured and bound the covering into an increasingly weatherproof and insulating mass. The economic implications extended far beyond simple material costs. While his neighbors faced regular expenditures for replacement shingles, nails, tar paper, and the labor time required for roof maintenance, Thatcher's total roofing costs after the initial installation amounted to zero. The prairie provided both the material and the maintenance system, requiring only the knowledge to select proper sod and apply it according to principles that worked with natural processes rather than against them. The thermal mass of 12 inches of earth had transformed his cabin into a structure that remained comfortable in both winter and summer, while consuming dramatically less fuel than conventional construction, proving that traditional knowledge could deliver measurable advantages that no amount of modern materials could match. The first serious flaw in Thatcher's sod roof system revealed itself during the spring of 1878, when a late March storm brought 2 inches of rain followed immediately by rapid snowmelt from the winter's accumulated drifts. The combination created more water than the prairie had seen in any single event since Thatcher's arrival, and his roof's response exposed a critical weakness in his understanding of earth-cover drainage. The problem manifested as standing water, pooling in shallow depressions across the sod surface, particularly along the lower sections near the eaves, where the roof's natural settling had created low spots. Instead of shedding water quickly like the wooden shingle roofs around him, the sod covering held moisture like a saturated sponge, creating pools that persisted for days after the storm ended. The additional weight of standing water combined with the already heavy sod load caused visible sagging in 2 of his oak rafters, and damp patches began appearing on the interior ceiling where moisture had penetrated the tar paper barrier. Worse, wind-driven rain during the storm had found entry points along the roof edges, where the sod blocks met the eave boards. Without proper weather stripping or drainage channels to direct water away from these vulnerable joints, moisture had worked its way under the sod covering and begun saturating the tar paper underneath. Thatcher discovered the infiltration when he climbed onto his roof after the storm and found soggy areas where water had pooled against the eave line, creating conditions that would inevitably lead to rot in his wooden roof deck. The failure forced Thatcher to confront a fundamental principle he had overlooked. Earth-covered roofs required active water management systems that wooden shingle roofs handled naturally through their overlapping design and steep angles. His relatively flat roof, built with only minimal slope to support the heavy sod load, lacked the pitch necessary to shed water quickly. The dense sod covering that provided excellent insulation also trapped moisture, creating a system that could hold dangerous amounts of water weight during extended wet periods. Standing Buffalo, a Lakota elder who maintained a winter camp near the settlement's eastern boundary, provided the solution when Thatcher approached him for advice about prairie water management. Standing Buffalo had observed the homesteaders' building methods with interest, recognizing that their techniques ignored principles that Plains tribes had refined over generations of building in environments where water control often meant the difference between shelter and disaster. The elder explained that traditional earth-covered structures succeeded because they incorporated specific drainage features designed to work with heavy precipitation and rapid snowmelt. Buffalo chip shelters and earth lodges used carefully planned slopes and channels that directed water away from vulnerable areas before it could accumulate dangerous weight or find entry points into the structure below. The key was not preventing water from reaching the earth covering, but ensuring it moved across and off the surface as quickly as possible. Standing Buffalo demonstrated the principle using a patch of prairie near his camp, showing how even slight changes in ground contour could direct water flow across substantial distances. A slope of just 4 inches over 12 feet, barely perceptible to the eye, would move water steadily toward designated drainage points, rather than allowing it to pool in low areas. The same principle applied to roof construction. Creating subtle channels and maintaining consistent slope would transform the roof from a water trap into a water-shedding system. Implementing the drainage solution required Thatcher to modify his existing roof structure, work that consumed most of April 1878. He began by adjusting the roof framing to create a consistent slope of 5 inches per 12 feet from ridge to eaves, using wooden wedges and shimming blocks to eliminate the low spots where water had pooled. The increased slope required repositioning several of his oak posts and adjusting the ridge beam, careful work that had to maintain the structural integrity while improving the water-shedding characteristics. Next, he installed shallow drainage channels running parallel to the rafters, created by placing narrow wooden strips beneath the tar paper at 18-inch intervals. These channels, only 1 inch deep but extending the full length of the roof, provided pathways for water to flow even when the sod above became saturated. The channels directed water toward the eaves where it could drain clear of the structure rather than pooling along the roof edges. Friedrich Kurtz, a German immigrant who had settled south of the territory, contributed another crucial element when Thatcher consulted him about waterproofing techniques used in European earth construction. Kurtz had learned clay mortar applications from builders who used sun-dried brick and earth plaster systems in regions with heavy rainfall. He showed Thatcher how to create a thin clay-based sealant that could be applied over the tar paper to create an additional moisture barrier beneath the sod. The clay-mortar mixture combined local clay soil with chopped grass and a small amount of pine tar, creating a semi-rigid layer that remained flexible enough to accommodate the seasonal expansion and contraction of the wooden roof deck. Applied in a thin coat over the tar paper, the clay mixture filled small gaps and imperfections, while providing a smooth, water-resistant surface for the sod placement. The technique added only modest weight to the roof system, while significantly improving its ability to resist moisture penetration. Thatcher also addressed the ventilation problems that had allowed humid interior air to condense against the roof deck and contribute to the moisture issues. He cut a 2-inch gap along the ridge line, running the full length of the roof and covered with a simple wooden cap that allowed air circulation while preventing direct water entry. This ridge ventilation system created airflow that carried moisture-laden air out of the roof space before it could condense and add to the drainage problems. The effectiveness of the drainage modifications became clear during the first major storm after their completion. In early June 1878, another heavy rain event brought 3 inches of precipitation in 12 hours, conditions that had previously created serious pooling and weight problems. The improved roof system shed the water completely within 4 hours after the rain ended, leaving no standing pools and showing no signs of moisture penetration at the vulnerable edge joints. Temperature measurements inside Thatcher's cabin during the storm showed that the drainage improvements had not compromised the thermal performance of the sod covering. Interior temperatures remained stable throughout the precipitation event, indicating that the water management system was removing excess moisture without allowing the insulating properties of the earth covering to deteriorate. The following winter provided the ultimate test when freeze-thaw cycles subjected the roof system to the expansion and contraction forces that destroyed many frontier structures. The drainage channels prevented ice dams from forming along the eaves, while the clay mortar barrier remained flexible enough to accommodate thermal movement without cracking. When spring arrived, Thatcher's roof showed no frost damage, no separation in the sod covering, and no signs of moisture-related deterioration in the wooden structure underneath. The water management system had transformed his experimental sod roof from a promising but flawed concept into a complete building system that could handle the full range of prairie weather conditions while maintaining its structural integrity and thermal performance over extended periods. The ultimate test of Thatcher's integrated building system came in the spring of 1900, 25 years after he had first laid sod over his unconventional roof structure. An extreme weather event struck the Dakota Territory that March, combining conditions that would have challenged any frontier building: 3 feet of accumulated snow, followed by 60-mile-per-hour winds that created drifts against north-facing walls, then 3 inches of rain over 4 days, followed by rapid temperature swings from 10 degrees Fahrenheit to 50 degrees Fahrenheit that caused explosive snowmelt and flooding across the prairie. The storm sequence created structural loads and moisture conditions beyond anything the territory had experienced in recorded history. Meteorological measurements taken at the Territorial Weather Station showed that the combination of snow weight, wind pressure, and rapid thermal cycling subjected buildings to stresses equivalent to multiple normal winter seasons compressed into 1 week. For the homesteaders who had built using standard methods, the convergence of extreme conditions revealed every weakness in conventional frontier construction. Samuel Korff's cabin, which had undergone 3 complete roof replacements since 1875, suffered catastrophic failure on the storm's second day when accumulated snow and wind pressure caused his entire roof structure to collapse inward. The failure began at the ridge beam, which had been weakened by repeated repairs over the years, then cascaded through the rafters as the distributed load exceeded the capacity of his patched and sistered framing members. The collapse destroyed most of Korff's interior furnishings and left his family homeless until neighbors could provide temporary shelter. Mary Wright's cabin survived structurally, but suffered extensive water damage when her 4th-generation shingle roof failed to shed the unprecedented precipitation load. Multiple leaks developed where years of thermal cycling had loosened the shingle attachments, and wind-driven rain penetrated through gaps that had been inadequately sealed during previous repairs. The interior flooding damaged stored grain, clothing, and household goods, representing economic losses that exceeded $200 in contemporary valuation. Across the settlement, the pattern repeated with variations but consistent themes. William Brenner lost half his roof deck when saturated snow created a point load that punched through weakened sheathing. The Kowalski family evacuated their cabin when interior temperatures dropped to 30 degrees Fahrenheit after wind tore away a section of their south-facing wall where repeated roof leaks had rotted the structural connection between wall and roof systems. Every building constructed using conventional methods suffered some combination of structural failure, water damage, or thermal performance collapse. Thatcher's cabin weathered the entire storm sequence without any measurable degradation in structural integrity, water resistance, or interior climate control. Detailed measurements taken during and after the storm showed that his oak post structure experienced 0 deflection under the maximum snow loads, with the tie beam system successfully preventing any wall displacement despite the unprecedented combination of vertical and lateral forces. The drainage channels that he had installed after the 1878 water problems handled the extreme precipitation without allowing any standing water to accumulate on the roof surface. Most significantly, the interior temperature of Thatcher's cabin never dropped below 54 degrees Fahrenheit during the coldest periods of the storm, despite the fact that he was unable to maintain his normal heating routine due to chimney draft problems caused by the extreme winds. The thermal mass of the sod roof system continued to moderate interior temperatures, even when the heating system operated at reduced capacity, demonstrating that the integrated design provided resilience that extended far beyond normal operating conditions. The economic comparison between Thatcher's approach and conventional methods became starkly apparent in the storm's aftermath. Neighbors faced reconstruction costs ranging from $50 for extensive repairs to over $300 for complete rebuilding in cases like Corf's collapse. The combined labor time for repairs across the settlement exceeded 400 person days, work that had to be completed during the critical spring planting season, when every day of delay reduced crop yields. Thatcher's post-storm maintenance requirements consisted of adding 3 replacement sod blocks where wind erosion had caused minor thinning, work that took less than 2 hours and cost nothing beyond the labor to cut new blocks from his own prairie. His total storm-related expenses amounted to 0, and his cabin was immediately ready for normal occupancy without any delay to his farming operations. The stark contrast prompted a fundamental shift in local building attitudes that had persisted for 25 years. Neighbors who had mocked Thatcher's dirt roof approach began asking detailed questions about his construction methods, particularly the structural techniques that had prevented the failures they had experienced repeatedly. Mary Wright, facing her 5th major roof repair, requested permission to examine Thatcher's drainage system and oak post framework, becoming the first local convert to earth cover construction principles. The lumber dealer, who had originally warned against the sod roof approach, admitted his error publicly at the spring township meeting. "I've sold enough replacement lumber to build 3 complete settlements," he told the gathering, "and John's roof still looks the same as it did when he first put dirt on it." The economic implications were unmistakable. Conventional building methods had generated continuous costs and recurring failures, while traditional techniques properly adapted to prairie conditions had eliminated both problems simultaneously. Word of the system's performance spread beyond the immediate settlement through the detailed reports filed by Thomas Green, the territorial building inspector who documented the storm damage for insurance and territorial planning purposes. Green's official assessment noted that earth-covered roofing systems showed markedly superior performance compared to conventional methods, particularly in extreme weather conditions. His report recommended further study of traditional building techniques that had been dismissed as primitive by mainstream construction practice. The documentation process revealed another crucial advantage of Thatcher's approach: knowledge transfer and replication. Unlike conventional methods that required specialized materials shipped from distant suppliers, the sod roof system used materials available on every prairie homestead. More importantly, the techniques could be taught through direct observation and hands-on instruction rather than requiring formal carpentry training or written manuals. Standing Buffalo, now in his 70s, observed the interest in traditional building methods with satisfaction that mixed vindication with pragmatic acceptance. "The earth teaches everything you need to know about building on the earth," he told Thatcher during one of their conversations that spring. "It just took your people 25 years to stop ignoring the lessons." The long-term economic analysis completed that summer showed that Thatcher's total building-related expenditures since 1875 amounted to less than $60, including the original construction costs. His neighbors had spent an average of $450 each on repeated repairs, replacements, and reconstruction over the same period, a difference that represented more than the cash value of most homestead claims. The proof was complete. Traditional knowledge properly applied to local conditions had outperformed conventional wisdom by every measurable standard, creating a building system that worked with prairie realities rather than fighting against them.